The next section for Chapter 8, I will give you some discussion about the ideal gas law and the various other related gas laws, and the partial pressure will come in a second recording after this one to keep them shorter for you. So the combined gas law is something that was shown or derived or discussed somewhat in Activity 26 in your Pogel book. It comes from relationships between pressure, volume, and temperature. And if any of those three variables is held as a constant, no change from set of conditions 1 to set of conditions number 2, it cancels out of an equation. So it simplifies your relationship, but it all goes back to the one that looks shown at the top here, P1 V1 over T1 equals P2 V2 over T2. We'll do some examples that I can show you here to see how these are set up, to give you an idea how these work. They're actually quite straightforward once you pay attention to what the equations are and how to identify which is pressure 1, volume 1, temperature 1, and label them carefully so that you don't mix them up as you set them into an equation. Sometimes you can predict intuitively what will happen in a gas law problem, but sometimes you can't because more than one variable has changed, and so you'll have to do some calculations to actually come up with an answer. Get your calculators ready. We'll be doing some of these together. These combined gas laws are all assuming that you haven't changed the number of gas particles, or in other words, the number of moles is constant. These are shown in a table in the text that looks rather crazy, but you don't have to panic about it because all of these will be given to you on an exam. Look at the old one on Blackboard, and you'll see exactly what kinds of equations are available to you. Just use them as you practice doing your homework. Okay, so let's try some examples and see where we need to go with this. Gases can be described as like things of steam in an autoclave where they sterilize instrumentation. The steam starts out at 100 degrees Celsius. It's going to be 1 atmosphere, which is sort of ordinary when you close the door. If you close it, the steam is heated up at a constant volume because the container is closed and doesn't change until the pressure gauge has an increased pressure of 1.3 atmosphere. The question then is, what is the new temperature inside the autoclave, having done this? Well, the primary thing you want to do every time with these kinds of questions is be very diligent to note all of the parts from your question and write them down with labels so that you don't plug them in incorrectly. Temperature 1 would therefore be 100 Celsius, and we'll stick it there. Pressure 1 is 1 atmosphere. Do not leave your units out. You'll be sorry if you do. Volume 1 is not a problem because volume 1 equals volume 2, so we can ignore that. Temperature 2 is the one we want to know, and pressure 2 is 1.13 atmospheres. Now, what do we use for an equation? The equation, I believe I have it shown here, is going to be T2 equals all of these parts put together. If you rearrange the P1 V1 over T1 equation, you'll get this version. And so for this problem, whoops, go back. Oh, I apologize. Now to continue. Set up your equation very carefully, and to do so we'll begin with T2 equals. It's much easier to rearrange the equation with the variable letters in it than to stick in the numbers and do the rearranging. So T2 will be T1, 100 Celsius, and my tool is getting slow on me again. Then times pressure 2, which is 1.13 atmospheres. And as I mentioned before, since volume hasn't changed, volume 2 equals volume 1, we will just drop that out of the calculation and divide this all by pressure 1, oh, handy number, 1 atmosphere. And, oh, what have we forgotten? We always have to do these calculations in Kelvin. So never mind whether they gave it to you in Celsius, you'll need to add 273 here, and the value of temperature is going to have to be 373 Kelvin, and otherwise your calculations will not make sense. They only work when you do them in Kelvin. So take that out, put in 373 instead, and then you perform a calculation with your trusty calculator. I hope you've got one handy and you can catch up with me and do it. Pause it while you do your calculations. If your calculator is consistent with mine, the answer I get is 421 Kelvin. 3 digits should be sufficient here. To be honest, this value up here at the beginning looks like only 1 sig fig, but as long as you're adding 273 to it, becomes a 3 sig fig value. So 3 sig figs are suitable in my answer. Just to verify what I have on my display. Whoops, that's supposed to be a 4. 421.49, so it doesn't round up. Call that 421 Kelvin, but let's see what temperature do we want to say. Let's convert that one to Celsius. So subtract 273 from it, and you get a new value, which is 148 Celsius. Quite a bit hotter, but not as much as you might have first thought. Be always careful to pay attention to your units because you'll be making mistakes that are not intended otherwise. Remembering the conversion between Celsius and Fahrenheit is 273 degrees. And that will quickly give you the answer that you need. All right, shall we try another one? So this time we'll just set it up. The answers aren't really important to us. It's how you set them up that it's the key. If you really want to see the answers, check with me later and I can give them to you. All right, so a gas in this particular example is under 1 atmosphere of pressure in a flexible container. So something with a movable piston, maybe a balloon, with a volume of ½ liter at a temperature of 393 Kelvin. How helpful, they gave it to us in Kelvin to begin with. And the gas is heated up, makes it hot. And the volume is going to expand because it got hotter. That's not surprising. What does the new pressure end up to be? Again, we'll have to come up with all of our pieces and an equation to relate them all. There's going to be T1, P1, etc. And the equation we need is a P2 equals type of equation. And so P2 equals P1 V1 times T2 over T1 V2. Well, what parts do we have given to us in this equation, in this question? Pressure 1, 1 atmosphere. Go back. Pressure 1 is 1 atmosphere. And then the flexible container has a volume of ½ liter, so that would be volume 1, 0.5 liters. And the beginning temperature is 393 Kelvin, so put that in, temperature 1. It's not any trickier than that, just be careful to label them correctly. The gas is heated up to a new temperature of 500 Kelvin, because someone has that type of reading, or they've converted it for you. And the volume expands to 3 liters, so that would be volume 2, 3.0 liters, and pressure 2 is the one we want to know. In this case, nothing's canceled out because you've had changes in both pressure and temperature, and so we're looking for and volume, so we're looking for the new pressure. So set it up carefully and make sure your units all fit in correctly. Pressure 2 then will be related to pressure 1 at 1 atmosphere, multiplied times volume 1, ½ liter, and it's supposed to look like an L, sorry, and multiply that times temperature 2, 500 Kelvin, and then we'll divide it by the other remaining portions. So we'll divide by temperature 1, which was 393 Kelvin, and then times volume 2, and volume 2 was 3 liters. So we'll put all that in there, but then check out your units, because then it will reassure you that you've got things set up correctly. So now that I've got all the parts written down, what can cancel? The liters cancel, Kelvin cancels, and what remains is only atmospheres, which is what you should hope to have for a value of pressure. So put it into your calculating device and be comfortable with your calculator so that you'll do these correctly when it comes to an exam. I will give you answers to some of these questions at the last of this recording. Okay, continuing to talk more about the relationships that are involved in these combined gas laws, is worthy to realize that the number of moles of a gas is related to the temperature and pressure, etc. So the volume is related to the number of moles by a graph that's shown here. They're proportional. The more moles you have, the greater the volume, assuming that the pressure and temperature haven't changed. And this is incorporated into the ideal gas law, but it's interesting to note this nice linear relationship. The more the moles you have, the greater the volume you have. It makes sense. But we use that in some other ways and think about it in terms of Temperature and pressure being the same, the volume is going to be related to the number of moles. And so if we think of sets of conditions that are common for pressure and temperature, then we can make some comparisons between samples more easily. These will be described as what we call reference conditions or standard conditions. And standard temperature and standard pressure are simply given a definition for some easy reference at being 273 Kelvin, namely 0 Celsius, and the pressure of 1 atmosphere. So those are described as standard temperature and pressure, a new interpretation of the letters STP you may have heard used somewhere else. So they're 0 Celsius, 1 atmosphere, or 760 millimeters of mercury. The result of that thought gives you this notion that 1 liter of any gas, assuming it's behaving as though ideal, at a particular standard temperature and pressure will always have the same number of molecules. And so 1 mole of any gas will have the same volume as long as we're at standard temperature and pressure. This leads to some interesting shortcuts in doing some calculations. They're kind of fun once you see the shortcut. Okay, so how do we use that? We're going to use it in conjunction with the universal or the ideal gas law. The ideal gas law, which was discussed in Chem Activity 26 about gases in the Pogel book. All of these are combined into one formula that some people like to put vowels into, but I just say PV equals nRT. It's easy enough to remember. Our activity gave us a way to realize what the value for R, the gas constant, is. 0.0821 to 3 significant figures with these incredibly clumsy looking units, but you get used to them the more times you work these problems. There is another way of stating this constant if you change the units of pressure. If you're given a question that has millimeters of mercury for pressure, then you would be speedier to use this value for R. You can convert the pressure instead, but this is a nice shortcut to having to do that. So simply choose the value of R that suits the pressure units convenient in your problem. Always make sure you use temperature in kelvins, volumes in liters, and then you'll have the right parts to relate things using the gas constant. Now, given the standard temperature and pressure, we can come up with a standard molar gas volume using the ideal gas law, because for 1 mole, which would be what we're looking for over here, and at a condition of standard pressure, 1 atmosphere, and standard temperature, which is 273, given the value of R already being known, we can calculate a volume for that. So how does that get calculated? The volume is going to be related to that equation. So PV equals nRT. You can do this. And from that, you might realize that volume should be nRT over pressure. And the pressure we'll put in at the bottom as 1 atmosphere. The number of moles that we're calculating the volume for here is 1. And then we'll multiply that times R, which is 0. Get ready for the number. 0.0821 with the units of liters, atmospheres over moles times Kelvin, and multiply that times the value of temperature for the standard temperature and pressure, 273 Kelvin. If you put all that into your calculator, and as you do, make sure you check your units. It's always wise. Atmospheres on the bottom cancels with atmosphere on top. Moles here cancels with moles in the gas constant, realizing that whole big thing here is the middle, the R value. And Kelvin will also cancel with the Kelvin value here, leaving you simply only volume unit. And the answer is 22.4 liters is the volume of 1 mole of any gas at standard temperature and pressure. We call that the standard molar gas volume. So that's a really useful number to know, and I'll show you how we can use that in calculations. So 1 mole of any gas at STP has the same volume, the standard molar volume, 22.4 liters, the molar gas volume. And as represented in the diagram at the bottom of the screen, whether you have oxygen or helium or fluorine or argon does not matter. 1 mole is going to have the same volume. What's going to be different is their masses, because the mole has a different mass for each of these gases. So a mole of argon is certainly a lot heavier than a mole of helium, but they'll still have the same volume. The neat thing is that you can use this as a conversion factor. It's a shortcut in doing some calculations, which makes for some very easy ones when you realize that. Seldom do we have to know how many molecules it is, but we'll talk about 22.4 liters being 1 mole for any ideal gas at standard temperature and pressure. Put it on your note card if you want to remember it, because I'm not going to give it to you. This is one of those things you should have to have noticed by now. Doing your homework, I hope you use this. So standard temperature and pressure, the standard molar volume for any gas, 22.4 liters, regardless of the gas. This is a nice diagram from your text. You might want to make sure you cement that in your thoughts as you study. Let's try some now. So how many moles of helium are present at STP at 22.4 liters? Well, I don't know. Let's think about it here. So the relationship I gave you was 1 mole is going to be equal to 22.4 liters at STP. So at STP we're fine. So let's start with the value given here, 2.24 liters, and that will be set up with a conversion step now. 1 mole on top is related to 22.4 liters, and you can look at the math here. Don't get out your calculator. This one's set up for convenience to realize that this should be just 1/10 of a mole of, in this case, helium gas. It doesn't honestly matter which gas it is, because any ideal gas will have this same property for that many liters and standard temperature and pressure. If you have 11.2 liters of a gas, then you can figure out how many moles you're going to have. Well, let's not try too hard. 1 mole again is 22.4 liters. So put in the numbers. And as usual, you should be paying attention to units, otherwise you get yourself in trouble now and then. And realize that the answer comes out to be moles, and 11.2 divided by 22.4 was again set up for convenience. This is 1/2 of a mole, 0.5. Notice the first one on this page, I didn't mark it explicitly at the time, but the units do also fit here. The liters again have canceled. All right, try something else. If you want to use that relationship and also incorporate grams into the question, it just requires a little bit more, but not something intensely difficult. So if you use a calculation where, in this case, neon is in a container that has 44.8 liters at standard temperature and pressure, how many grams will that be? Well, start with your given value and start applying conversion factors until you get to something that will get you to grams. So 44.8 liters, neon. You need to pay attention to what the gas is in this case, because we're going to end up with grams. And first of all, let's go back to the same conversion we had on the previous examples. So 1 mole is still 22.4 liters for any gas at standard temperature and pressure. And that allows us to get from liters to moles, but we want grams. So we need another step that allows us to cancel out moles of the gas and relate it to grams. Well, this should look familiar to you, because there is a very common conversion factor that has grams per mole, and that one is described as molar mass. And so you find your trusty periodic table wherever you have one handy, look up the molar mass of neon, and the molar mass of neon is 20, at least in round numbers, that's close today, and we'll call it 20 grams, and then you do some math here. So the math isn't too bad, because again the numbers are set up for convenience. 44.8 divided by 22.4 is really only 2, and so 2 times 20 gives you, put the 2 over here, an answer of effectively 40 grams of the gas, 40 grams of neon. So not so bad. Let's try another. This time let's try figuring out the volume given 22 grams of carbon dioxide at standard temperature and pressure. Well, start out with the value that you're given, the 22 grams, and think about where that's going to go. Well, we can't use the standard molar volume yet, because we need to first find the molar mass and then convert to moles. So if you've done this somewhere before, the molar mass of carbon dioxide should somewhat sound familiar to you. It comes up from various places. So carbon dioxide is going to be a 1 carbon for 12 2 oxygens is 32, and so that's a total of, magic mathematical wizards, here you go, 44 grams per mole for CO2. All right, we'll plug that into our calculation. Once that's plugged in, with the units set up so they cancel, the grams of carbon dioxide cancel there. But now we have moles and we're looking for volume. Continuing with what conversion factor seems convenient, I bet we know something that relates moles that need to cancel to volume. And let's try the standard molar volume again. So it's like the one at the top of the screen here, except you got to put the units in the right places. The 22.4 liters needs to go on the top to get us a volume as an answer because we wanted moles to cancel out. And so the moles cancel, and this becomes a math problem. Again, I do these for convenience so we don't have to spend all of our time punching buttons on a calculator and make it more obvious to you. 22 divided by 44, well that goes into 44 two times, so it's 1/2. And so 1/2 of 22.4 liters is not going to require a calculator either. That would be 11.2 liters. All right, that's a couple of examples of some easy uses for calculating volumes or grams or moles with standard molar volume given gas at STP. Good one to remember. My circle didn't work there, sorry folks. All right, a couple more examples. I think folks like to see some of these, but really once you get used to them, they're not bad. What if you have 5 grams of carbon dioxide, the vessel is 10 liters, and 350 Kelvin is the temperature. We want to know pressure. Well, what shall we do to set this one up? The first thing to identify is what do you have, so you can recognize what equation could be useful to you. In this setup, we have a number of grams, and grams isn't probably in any of our equations, so think about that for a sec. And then we have volume, and we have temperature, and we don't have a second set of volume and temperature, so this is not a combined gas law with V1, P1, T1 type numbers. Instead, we should use the ideal gas law and come up with a pressure that is related to nRT from PV nRT divided by volume. Now, what do we not have? We don't have N, but N can be derived from the number of grams. So let's come up with N. 5 grams of carbon dioxide. From the previous example, you will note that the molar mass of carbon dioxide was already given there, so it's 44 grams of carbon dioxide per mole, and that comes up with a number that comes out of your calculator. Punch it in, see what you get. I encourage you to work these problems in tandem with me, so pause the recording momentarily while you put your values in the calculator, and then you'll be able to compare yours without cheating, without using just mine. The number I derived from my calculation looks like 0.1136, whoops, another one in there, 36 moles of carbon dioxide. How many sig figs do you want for this calculation? This one should be a 3 sig fig value. 3 sig fig value, oh, the first one's only 2. So we only have 2 sig figs going through to the end of this calculation. Leaving 3 in for the number of moles is completely fine. It's a very good way to go. Instead of rounding off at the beginning, you should round off at the end. So putting in the values given, we'll put in 0, and remember that one's not significant, 0.114, close enough. Should be okay for this calculation. And then multiply that times R. And R, it takes a minute to write because the units are very clumsy. Be sure whenever you put in R, you put in all the units, 0.0821, I forgot the 1, liters, atmospheres per mole, Kelvin. That one looks a little funny now, sorry. And then we'll add in the last value from the question for the numerator, the 350 Kelvin. And pay attention as we finish setting this up to make sure all the units fall into place, otherwise you may have overlooked something. The part that goes on the bottom is volume, 10 liters, no big deal, can do that. So put in your 10 liters, and I don't need to write the 0.0, it doesn't really matter. The moles from this first term cancel with the mole in R. The Kelvin cancels with Kelvin at the end. The liters cancels with the denominator with R, those two together. The value that remains should be pressure. Again, all we really want to do is set these up, and I will give you answers to these at the conclusion of this recording. I hope you work them through on your own. The second part of this page, we have another example with neon gas this time. And it's given a pressure of 1.05 atmosphere, that's P. And the temperature is given at 303 Kelvin, so that's T. And the volume must be the 10 liters. And so we want to find out how many moles are present. Again, your challenge is to realize what equations are available to you and which one suits the information provided. In fact, this one is quite analogous to the one at the top of the screen. You're going to use pressure, volume, temperature, and R, and number of moles. So it's this time we're going to calculate the number of moles present. And so given the PV equals nRT relationship, PV so rearranging the equation, you get N equals RT over PV. So we'll write in all the parts again, but be very fastidious, very disciplined to put down all the units because it pays off tremendously, especially in gas law calculations, because now and then they'll give you pressures in different units or they'll give you temperatures in different units, and you'll get yourself in trouble if you've forgotten how to do them. So liters, atmospheres, and mole per mole Kelvin, sounds really goofy, but that's the way constants go, will be our units on R. The liters, atmospheres divided by mole Kelvin, same old thing. Then temperature is 303 Kelvin, and on the bottom we will put in the pressure and the volume. Pressure being 1.05 atmospheres. The volume given at 10 liters. Again, being careful to read your question and make sure you know what pieces of information are available to you. Paying attention to units, as always. I'll be a stickler about that. I'll remind you as much as I can. Liters should cancel. Atmosphere cancels. Kelvin should cancel, because we've got Kelvin in the R value and also in the temperature. And that leaves you with simply moles, which is what you should be aiming for in this question. Otherwise, something is set up incorrectly. Again, I'll provide you the answers to these at the end of this recording. Now I'll give you one more example that has significant more parts to remember. This is very much like one in your Poggle book, so I hope you can find your way through this example and see how it's done. If you are given a number of grams of ethane, C2H6, and the atmosphere is pressure, and a temperature, we can calculate the volume this should have using the gas laws that we know. In this case, the values you're given are grams, atmospheres, temperature, so it's related to the one in the previous examples where we needed to come up with grams, use grams to come up with moles, and from there use the ideal gas equation. The ideal gas equation to find volume is going to be volume equals nRT over pressure. So then we'll have to come up with N first. So let's do the molar mass. First step to use that is finding C2H6 has a molar mass of 2 carbons, which is 2 times 12 or 24, and 6 hydrogens is close enough to 6 for this calculation. We'll call that 30 grams per mole. And we'll set that up using the number of moles or grams given. That'll be a little bit of a funny number, but that doesn't matter. 359 grams of C2H6. We don't have another one in here, so let's leave out the formula. And that will be 30 grams per mole. So the grams needs to go on the bottom where it cancels, and the moles on top. Get out your trusty calculator, which should be at your side by now doing these questions, and come up with an answer for the number of moles. Again, I hope you paused the recording long enough to do your calculation. That's what I did actually. And my number I come up with here is 11.9666, lots of sixes here, So let's just call it 667, and that would be moles. How many digits do we really want for this calculation? This is sig fig's problem again. So you got 3 digits here, and you have pressure with 3 units. The temperature only has 2, but this is in Celsius, so recall that we're going to add another digit by converting it to Kelvin, and that's totally fair. So we will end up with 3 digits in our calculation for those values. And so let's take this one to 4 just so we don't cheat our values any. So let's call it 11.47 moles. All right, now let's get that temperature into Kelvin. So we have to add 273 to the 75 to get the right number to stick into the calculation. And with your trusty calculator at hand, or doing it like I'm doing it now, 5 plus 3 is 8, 7 plus 7 is 14. Carry 1 over to the next column, that's 348 Kelvin. All right, you can do that. Trust me, you've tried this before. And it just has a little practice. So the volume will be equal to what? We'll put in the values. So 11.47 is the number of moles we calculated using that molar mass. And then we'll put in R, our favorite funny unit of the chapter. We'll get good at it eventually. 0. Just as you see it here, 0.0821 liters atmosphere per mole Kelvin. And then the third value on the numerator will be the temperature, 348 Kelvin. Plug it in as usual. The denominator becomes what's left, namely that we haven't used, pressure. And so pressure is just a number, 0.658. We don't care what they give us. We can use a calculator to find an answer. And that is again in atmospheres. So that makes our calculations without any confusion in the units on the value of R. Trust me, you'll see some on the homework that won't have this unit for our pressure, and you'll need to pay attention to that to use R correctly. Okay, units making sense. Moles still cancel. Atmosphere still cancels. Kelvin still cancels. And that should give you an answer in liters, which is the goal for this question, is to come up with a volume. And get out your trusty calculator, see what you get. I just realized I wrote that number down wrong because my writing is so funny with this tool, but that should be a 9 on the volume. 11.97, not 4. Apologies for the technical difficulties here. The answer that I come up with on this one is 519.6. And let's see, how many figures did we say we wanted on our answer? 519.6. And it comes out quite evenly, 0, whatever after that. Again, 3 sig figs for your answer. Paying attention to sig figs is a good practice. It's a good habit. It's chemistry class. You got to learn a little bit about significant digits. So 3 significant digits here would be an answer of 520. And of course the unit on this answer should be liters, just as predicted. And now I'll give you the answers to the calculations on those previous slides. If I can remember how to use my tool correctly, helps. The answer on slide 43 was 0.3265. It's a 2 sig fig answer, so we report that to 0.033. 0.33, pardon me, I said it wrong. And before you panic completely, I was just reading the wrong answer when I wrote that one down. So here's the 2 sig fig answer for this question was 0.212, or take it down to 2 sig figs, call it 0.21 atmospheres. Okay, you heard the answer to the first part of slide 52 before, 0.33 atmospheres. Now the second part was N, the calculated value of the number of moles, which turns out to be to 3 significant figures, a value of 2.37. I hope this helps you. Good luck on your homework.